My name is Alex Merose. I'm here to talk to you about why machine learning people should think about databases. I just started at this new company called Open Athena, and as a result, I don't really have a package for you to start on GitHub or a service that you should consume. So instead today, I'd really like to take a 10,000-foot view at cloud-native geospatial, and maybe instead, even beyond that, this moment in technology that we're in right now. And this talk is lessons from AI weather models, because in a previous life, I worked on building AI weather models at Google Research. So, on that note, maybe a lot of people aren't familiar with what's going on with AI weather models, and I could tell you and describe it, but I actually would let Vox Media do a decent job, and if the audio doesn't work, I will happily dictate it, this really great reporting.
On September 11th, 2020, weather predictions in the northeast of the U.S. sounded like this.
All eyes are on Hurricane Lee.
The storm has strengthened back to a Category 3.
We're expecting it to make a northward turn over the next few days.
By September 16th, after being downgraded, Storm Lee made landfall in Nova Scotia, Canada, flooding roads, downing trees, and cutting out power for tens of thousands of people along the East Coast.
Machine learning system is, and that's kind of the thesis of my talk, is that these foundation weather models are differential databases. There's still and I'll explain kind of what this means in a moment, but the high level idea is that machine learning has turned weather forecasting from a batch job run on supercomputers into a query on the latent space of weather data. And let me define a few terms, because this is kind of a big concept, and this is really all I really want to talk about today. What do I mean by differential? So let's take a step back and let me explain what differentiable programming is. In programming, we have data, and we have code, which are typically, you can think of as functions on data. And if I had a really quick, few-word definition of machine learning is a combination of data and code. Like, you might call this learning from experience. You also could call it, especially in today's world, over-parameterization. But like the components or the capability in a programming language or in a computing system that makes ML possible really is differentiation. And Karpathy wrote about this in 2017 when he called software 2.0, that software 1.0 is like I'm manually writing a program, and software 2.0 might be the combination of optimization, hardware acceleration, and like the missing component is like differentiable programming. That kind of combination is really the essence of machine learning. And I believe that the core capability that's really missing is this is the essence of differential programming in one definition of what machine learning is that's pretty inclusive and abstract. And then you might ask, well, what is a database? And I've come to learn in reviewing some systems literature that the lines between software systems are actually really blurry. Like, we normally think that there's like a kernel, like an operating system, and then maybe a database is a pretty fundamental layer on top of the kernel, and then an application space. And maybe a feature of the application is machine learning. Like that's how I would draw a diagram in most systems. And then I read about DBOS. So like researchers at top universities and hyperscalers have created an operating system on top of a database, which is crazy. And it turns out if you look at the hardware environment of today, which is mostly the data center, there are actually advantages of using like a multi-store, like Polystore, like Postgres and in-memory database as an abstraction layer to build an operating system, because it offers really great advantages in performance concurrency control, to then build user applications on top of that, like a Spark cluster or Lambda services. So maybe we actually really could draw the lines somewhat where we wanted. And Karpathy again took this liberty when he tweeted this idea of an LLM OS. He said that if you squint and you look at the diagram of large language models and the ecosystem of tools being built around it, what it kind of reminds me of, and it reminded him of, is like a CPU architecture, like the MIPS architecture we learned if you took a computer science undergrad in college. of understanding what like the basics of an operating system is. Instead of a hertz rate of a clock rate of a CPU, you have tokens per second. Instead of RAM or main memory, you have a context window. And instead of disk, you have a vector DB as a part of a RAG application. And I actually challenge Andrew Karpathy, calling this system an operating system. I think a better fit for this is a database system, because data, as I'll kind of establish later in my talk, has primacy over compute. And you know, if we really look at the definition of a database, we might look at this textbook by many authors, including Michael Stonebreaker. You know, this is referred to in the Red Book, Readings in Database Systems. And this diagram comes up, and you know, Michael Stonebreaker reflects upon this diagram, and like this textbook was published in 2007, I believe. But he says that even all the way from System R, where SQL was invented by IBM, all the way to the present, and the hardware environment and technologies have radically changed. And there's been all these hype cycles and explosions in tech, but a database mostly looks like this diagram, and the components change, but like you will have concurrency control system, you'll need to manage state, you'll have a query engine, you'll have to have a client to be able to read your store of data and manage catalogs, you know, et cetera, et cetera. And I think that's really powerful, and actually a really good analogy for cloud-native geospatial, because cloud-native geospatial, the ecosystem is database. Instead of Postgres, where the hardware environment of the time is a single desktop, we use the operating system of today, which is the cloud. And in the cloud, where you have a separation of compute and storage, you actually have the abstraction of every type of component of the operating system to a highly scalable service, and you kind of pick and choose the parts of a database a la carte that you really need for the application that you have. You know, Xarray is a really good abstraction on the new physical storage system of today, which is the array, and that may be a better SQL. You know, Michael Stonebreaker thinks that SQL is the COBOL of the 2020s. Dask is a really good query engine, and so is Beam, and so are many, many other systems. We have catalogs in the Stack and the Source Cooperative, IceChunk and TensorStore, and maybe Earth Engine. All these systems cover one or many different boxes, but you know, these systems definitely deal with concurrency control really, really well, and like the raw format. You know, a lot of people say, for example, that S3 is a new database. Where's S3's query engine? You know, I might use DuckDB for the query engine, and that kind of analogy, I think, really means that an ecosystem can be a database, and the ecosystem we're all a part of are really just database technologies. But I think what's really exciting is that in this like 50-year history of computing, of this diagram mostly looking the same, I think really in the last 20 years, if not like right now, we actually might have a big contribution in the history of computing. I think AI is so important that we can actually add a new box to this diagram. I think we can add a box, and I call it a semantic engine. And it's the addition of this box, of a database that you can choose a la carte, is the ability to do differentiable programming on top of the data store. And the semantic engine is made of lots of parts. You know, maybe you have a semantic index, which is like a vector DB, and maybe you have like the core semantic query engine, which is like a AI weather model or LLM or all these types of systems. And I think these components are radically iterating right now, but I think will eventually kind of coalesce into a solid, long-held abstraction, and think about it as almost like normal technology, kind of like how database systems were once radical new technologies and then slowly matured, and we slowly had things like, you know, the ACID transaction become standardized as a part of the stack. And I think that differential database is the right way to think about this, because with this surplus of compute, instead of a numerical weather system prediction being, you know, most of the time is step-by-step simulating physics every point in time until we get 10 days worth of forecast that takes 6 hours to compute, most of the complexity of the system, most of the gravity and hard part of the system that's hard to do is in the data store, and its optimization and lending itself to the hardware environment of today, which is the GPU or TPU, not in the compute layer, which is just, you know, a scaled-up transformer of you know, various ways to make it all work, to work with the domain of media that we are, in this case, atmospheric physics. Most of the system is the data, and I think we actually should maybe, like I argue that we should think of the differentiable programming part, the machine learning inference, as just an extension of a query. Like we might say, joins and aggregations on top of joins are two steps of the query. The last step might be a semantic, a layer of inference that happens on top of it, which is a semantic understanding, which is a combination of not just compute or code, but also code and data. And anyway, I think that the system and not the algorithm is what really is this fundamental to what's led this explosion in AI weather models. This is a diagram of from Stefan Rasp, who created Weatherbench 1 and many other systems in AI weather models. And he posted this on his blog. And if you look at kind of the history, I don't know if I have a cursor here. I'm really bad at cursors, but like, Weatherbench 1 was released, and there was a slow amount of models, making progress. This is relative score to physics models, to the ECMWF forecast. It wasn't until data was made available in a cloud-optimized format that you really saw an explosion of AI weather models and a lot of new development of these types of things. And it's a really particularly exciting moment now because Aardvark on the other corner and Fuxi, they're end-to-end physics-based observations. They go directly from raw Earth observations to a forecast of a system. And they're performing right now about as well as the physics emulators did when the initial data was released. And I guess this is why I say to this group, we all have an opportunity as a community to build the important parts of the database system to enable a new radical development of AI weather models. And I think that the data is so significant in this AI weather model system that we almost can think about it as a new database system. So why should we think of ML as databases in conclusion? It's normal technology, but that doesn't mean it can't be world-changing. Electricity is normal technology, but it totally changed the world. I think thinking it as a database system will help us build better ML systems. The formal methods of SQL has made managing data so robust and effortless, and ML is, an unfortunately really difficult and messy process, and I think we could expect better of our ML systems. And I think last and in conclusion, it's centered on data, and I think that's the core part. If we should be reframing AI, even Gen AI, they're all machine learning at the end of the day, as data systems. Sorry about that, firm tap. So thank you so much. That's why I think if you're a machine learning person, you should think about databases. And these are the lessons that I draw from AI weather models. Thank you so much for your time, and I will now take questions.
So for a lot of the models, for the machine learning models, it's not the inference that takes the compute, right? It's the training of them. So how does the training time of these models compare to actually the run times of the physics models, which I guess would be more the inference bit?
That's a good question. You have to kind of maybe incorporate developer time, maybe included in that, but it takes 2 or 3 weeks to train a large-scale AI weather model, depending on what you're trying to predict, whether it's a medium-range weather model or it's short-term. The short-term models have high-resolution data, so they're typically really big models. GraphCast can fit on a desktop computer, but MetNet takes 30 TPUs to train over 3 weeks. But it's just, you do that once and you learn it directly from data. And then that's all you need to do. Maybe you need to fine-tune a little bit when you have new data as the climate changes, because that is a factor that is important. So it's, if you don't, so it's weird in terms of, it's kind of in some sense, you're automating the building full of physicists and climate scientists' work to, the hyperparameter tuning and writing the model, and then the 3 weeks of training is one way to think about it. I think of machine learning as metaprogramming, really at its core. Anyway, I just think that the costs are significantly lower, they're more efficient, and I think that, I'm not sure if I totally answered your question, but I hope I did. Thank you so much.